Thank you. So I'm Jonna, and I'm here today with Embedl. And at Embedl, we are experts in deploying models to the edge and optimizing models for resource-constrained devices. And this is exactly what we're going to talk about today. More of a focus on generative AI, on how to deploy generative AI, what are some of the challenges, and how we can enable it today. My goal for this presentation is to compress the knowledge we have gained at Embedl over the last couple of years into a 20-minute presentation, and hopefully each and every one of you gets something out of this. So we have 3 key takeaways. We're going to see how local AI can enable secure and real-time performance already today. Some use cases, maybe with SenseAct you have just seen. We will see some of the challenges, one being that smaller models aren't always faster, and optimizing models for the edge is not an easy task. And then at the end, we're going to have a look at a case study we did, where we optimized Llama 3.2 for Qualcomm, a mobile chip. Great. So since we are all here at Gaia, I think each and every one of you has some idea of where to use AI today and where to use AI in the future. And I think everyone wants to have real-time analytics. You want your model to be fast, and especially in, for example, autonomous driving, you want to have ultra-fast processing. We've just heard if a child jumps in front of the car, we want the car to react right away and not wait half an hour. Then on top of that, when we have seen previous presentations about military applications, for example, where connectivity is not always given, and it is a luxury to have. And even if you are connected in a way, you still want to be secure. So you want your models to work even when you have low connectivity or no connectivity at all. So in summary, we want local AI. And, oops, yes. So local AI comes, of course, with a couple of challenges. It's not just taking your model and plugging it in and being happy. So when you take your big model, you may be trained on a cloud, trained on an A100 or H100 NVIDIA GPU, and deploy it on a small smartphone, maybe on an NVIDIA AGX Orin, you come with strict requirements. You have limited memory and compute. You want to have ultra-low inference latency, meaning you want your model to execute as fast as possible, and you want to have minimal power consumption. So in total, we're looking for models that are highly accurate but smaller, that are faster, and that maximize hardware utilization. We are essentially looking here for the unicorn. And on top of all those requirements, deploying to the edge is not an easy task. So on the edge, we have a wide range of hardware vendors to choose from and a wide range of hardware architectures that matter and that affect how your model runs on the hardware. So yeah, deploying a model on a car, this is perhaps not how it should look like. And when we think of LLMs, we think of huge models. And just taking them from the cloud, taking ChatGPT and deploying it on a car is maybe not what we want to do. And maybe taking a step back and looking at the development of language models in general. At the beginning, we have seen a big rise in model size. There, the challenge was to get the best model out there, to improve accuracy, to improve performance as best as we could. And at that time, we did it by just making models larger. But in the last just couple of years, starting roughly 2024, the focus has shifted, or focus got add-on with edge deployment or deployment of models in general and having faster inference, maybe saving some money. And here we have seen now a big rise on small language models. Nearly every couple of months, you see a new model coming up. And today we're going to talk about 2 of them. One of them being Llama 3.2, which was released September 2024, roughly half a year ago. And the other one, quite recent, Gamma 3, just released last month in March. Yes. So let's maybe quickly introduce those 2 models. and starting with Llama 3.2. And this was released by Meta, and it was released with the catchphrase, revolutionizing edge AI and vision with open customizable models. And at this point, the main goal was to develop models that fit onto edge and mobile devices. And they've used structured pruning, that is a model compression technique, and knowledge distillation. In just 2 slides, I'm going to explain those 2 techniques a bit more, so be patient. But let's maybe look first at how Gamma 3 proposed their model. So Gamma 3 is from Google DeepMind, and last month they released it with the catchphrase, the most capable model you can run on a single GPU or TPU, and also here made to run fastly and directly on devices where we as AI practitioners need them most. And on top of knowledge distillation, just like Meta used or did, they also did some architectural changes to the network. So as promised, a very quick intro to some of the model compression techniques used here. Of course, there's a wider range of them, but some main ones to make models smaller. So from left to right, pruning being a technique, for example, used in the Llama 3.2 to reduce the width of the network. And usually you maybe remove some channels of the network, some attention heads, for example, and thus making the model smaller. And what goes really well with pruning is a technique called knowledge distillation. And in knowledge distillation, you have a large teacher model and a small student network, in this case, oftentimes the pruned network. And then you can use the large network to distill the knowledge to the small student. And then finally, when it comes to deploying those models, oftentimes you want to reduce the precision level per layer or for the entire model. And when you train the network, often in floating point precision, but then for deployment, we usually go lower to integer precision and thus speed up the network and also reduce its size. Good. So let's get on with one of the key takeaways today. Are smaller models always faster? So now we have seen 2 examples where we simply made, or not simply, but we made the model smaller and thus hopefully it gets faster. So let's maybe test out this hypothesis and have a deeper look at that. And I want to look at an example in the computer vision area. And you're maybe familiar with ResNet 18 and MobileNet v2, both of them being quite popular, nowadays relatively old, but still well used or widely used vision models. And by themselves, they are often used for image classification. And on ImageNet, a typical image classification dataset, for example, containing an image of a dog, and then you expect the output dog, they achieve roughly the same accuracy. However, the ResNet 18 is significantly larger than the MobileNet v2, so in terms of floating point operations and in terms of number of parameters. And let's maybe just try it out and deploy those 2 models on a Raspberry Pi you're all, I guess, familiar with, or at least have heard of, which is a CPU type of device. And let's maybe do a quick vote. In the afternoon, I think it's nice to get a bit of the power up. So if you think that the MobileNet v2 is faster than the ResNet 18, meaning that it can process a single image in a fewer time, in a shorter time frame than the ResNet 18, just raise your hand. So, okay. And if you now think that the ResNet 18, the larger model, is faster on the CPU, just raise your hand as well. Okay. So quite even, maybe a bit more on MobileNet v2, but quite many on ResNet 18 as well. And maybe I fooled you a bit in triggering you and saying not every smaller model is faster, but in this case, the smaller model is indeed faster. So the MobileNet v2 is indeed 4 times faster than the ResNet 18. So it seems like model size correlates quite well with speed. And maybe let's to sanity check ourselves. That's what we like to do in research. Let's maybe look at another example. And now I'm not doing a voting, because now I think you will know what happens. So in this case, now the main part comes. The WestNet 18, the larger model, is faster than the MobileNet v2. So now on the left-hand side, we have deployed both models on an NVIDIA GPU, the NVIDIA R1 Nano, also a very powerful edge device. So that is a bit strange. So it seems like smaller models are not always faster. And for those two model architectures and for those two hardwares, there's a good explanation. So looking at the architectures of both models, and starting with the larger WestNet 18, this is a very traditional computer vision model consisting mostly of dense convolutions that are the typical convolutions and that are large parallelizable matrix multiplications. And that already sounds like it's great for a GPU. And thus, the WestNet 18 performs really well on the NVIDIA Jetson. On the other hand side, MobileNet v2, if you remember the paper, MobileNet, it was made for mobile devices. And in the context of the paper, mobile was defined as CPU-type devices. So this network consists mostly of depthwise separable convolutions that are many small sequential computations and is great for a CPU. So here we see an example where it truly matters what hardware you choose and what model architecture you choose, and it needs to align. And maybe you don't feel that it was intentional to make you raise your hand at the wrong point because you learn best by making mistakes. So yeah. Good, so now we got some learnings from computer vision. Let's maybe take those learnings to our Gamma 3 versus Llama 3.2 observation. So looking at the architecture of those two models, the Gamma 3, I now picked both the 1 billion parameter sizes, but to be precise, the Llama 3.2 has even 1.26 billions of parameters, since officially they, for some reason, don't include the head in the parameter count, and thus the Llama 3.2 is even 25% larger than the Gamma 3. But looking at the architecture, so the Gamma 3 is quite thin and deep, and the Llama 3.2 is wide and shallow. And wide and shallow often sounds like, maybe it's nice for a GPU. So maybe even though the Llama 3.2 is larger, even 25% larger, maybe it will perform quite well due to its maybe more favorable architecture. So let's test out this hypothesis on a NVIDIA RTX 3500. This is now just a laptop GPU, since we did those experiments just a couple of days after the Gamma 3 was released. But just taking those two models and deploying them or running them on this GPU, we see that running them in FP32 in full precision, they roughly get the same latency, or in this case, we don't say latency, we say token generation rate on how fast the models can produce tokens per second, and a higher number is here, of course, better. So even though the Llama model is significantly larger, or in the time, yeah, it is quite large, they roughly have the same speed. But taking this further and looking now on the last compression technique I introduced just a couple of slides back, which was quantization, let's see what happens when we quantize those models. And we see the Llama 3.2, the blue bars, it makes good use of quantization. So when we reduce the precision, the bit width, to bfloat 16 or in 4, we see a speed up as expected. So we can process, the model processes its output faster. However, for the Gamma 3, we don't see a speed up at all. And if you remember, I said when I introduced Gamma 3 that on top of using knowledge distillation, this model also introduced some new architectural changes. And at the time of making those experiments, and I think even today, we see a lack of support for Gamma 3 and those architectures. So the kernels that run on the hardware cannot make use of quantization and of the speed up for reducing the precision. But I think maybe not in the coming days, but in the coming weeks, this will likely change. So it's a bit of, you also not only have to build a good model, you are also a bit dependent on what the hardware vendor and what tooling you have available and what is supported on the hardware. Good. So now we have seen Llama 3.2 and Gamma 3. Let's maybe look at how we can take all those learnings, all those advices on how to optimize models for the edge into a case study where we optimized Llama 3.2 for Qualcomm. And in this case study, we looked at, again, the 1 billion Llama 3.2 model, which is, as I said, mobile friendly. And we looked at the Snapdragon chip from Qualcomm, which is, for example, you're maybe not familiar with the particular number of this chip, but you're maybe familiar with the Samsung Galaxy S24 Ultra, which is one of the newest flagship devices from Samsung. That's where, for example, the chip is used. And internally, or for our research team, the challenge was, can we prune without access to the original training data? Can we optimize this model for this hardware? So what we did, we used hardware-aware pruning and produced a compressed Llama 3.2, which is not only mobile-friendly, but also Qualcomm-friendly. And let's maybe jump right away to the results. So we see now a couple of bar charts, but let's maybe go left to right. So on the left-hand side, we see the familiar token generation rate, and which is also, of course, the higher the better. And here, by using hardware-aware optimization, we were able to get a 31% faster token generation for the Llama 3.2. And all of those results we see now are within 1% accuracy drop or evaluation drop, looking at some evaluation metrics for LLMs. Then another metric that is quite widely used is the prompt processing rate, how fast the LLM can process the input. And also here we were able to get a 25% faster network. And then finally, looking at the total initialization time in seconds, also here 126% faster. So quite significant speed up given the restrictions we told ourselves of not having any training data, not wanting to do any significant fine-tuning on the networks. But by taking the hardware quite into account, you're most of the time able to take out some or get some optimization and speed ups for your network. So that is, we are getting towards the end, and I hope every one of you got something out of this, but maybe as a quick summary. So we have seen how local AI can enable a secure and real-time performance, and that we maybe want to have local AI, and maybe you already have some ideas where to bring your AI from the cloud to the device. We've seen that some of the challenges, smaller models aren't always faster, and then we have seen a case study with the Llama 3.2 on Qualcomm. Thank you so much for listening.
It was great, Jonna. Thank you so much. I really enjoyed the reality check and the little quiz. Indeed, I just wanted to ask you if you can share, if there are any more misconceptions or misunderstanding really regarding this field.
One issue I see is that even today, deployment is seen as an afterthought. Deploying models sometimes is just an implementation detail. And I think every engineer in this room can agree with me that it's not. And maybe we should talk a bit more to the managers that we should have more time on properly having a good deployment setup and taking more time really figuring out what works best on our hardware we have. So that's what we might take on this.
Makes sense. Thank you. And we can take a couple of questions from the audience. Let's open it up. I think I saw. Yes.
Yes, thank you very much for the nice talk. So you mentioned that it really depends on the hardware that you're deploying your model, if the model is faster or not, and you show some result. But are these results based on try and error, or do you have a recipe when you see, for example, Llama 3.2 architecture and like the hardware you have that you're going to deploy on? Then you see, okay, this is going to be good for this hardware or not, or we need to choose Gemma, for example, or is there a recipe for it?
So and so. So depending on the stage you are in today, if you're in the stage of choosing a hardware at all, then there are different benchmarking tools that help you understand different hardware, like how they act or how your model acts on different hardwares. Maybe we should have a chat afterwards because we have such a tool. But yeah, I think it is a bit difficult to make suggestions in general. But like in this case, having wide models is usually better for certain hardware. Having dense convolutions is usually good for GPUs. Mobile net type architectures are good for CPU. But this is, of course, right now expert knowledge. And with our optimization tools, we kind of try to bring our expert knowledge to our customers and try to enable them do those optimizations themselves without having us in the loop. Yes, so it is definitely a challenging task to bring this into a tool, but they are definitely in our algorithms we use. Like you do usually a profiling of the hardware, and that will kind of influence how the algorithm and optimization works on your network.
Thank you.
Thank you very much. Great question. Do we have more questions? Yes, a lot.
Thank you. Very interesting. I'm curious about if you optimize a model for a Snapdragon. I have an old 750G Snapdragon. Would it work on multiple different versions, or do you need to optimize for each specific Qualcomm chip?
It depends how much they differ and what is, so for example, if I have, I'm not sure how much our two Qualcomm chips differ, but for example, if you have different Tensor RT versions on your NVIDIA or different QNN versions on Qualcomm, that's the inference framework. Of course, is usually fine, but you would get better results if you have the right pipeline from the start and to collect data to influence your algorithms and influence your optimization algorithms on the right hardware and on the right inference tool chains and versioning. So as a ad hoc, just testing things out, it definitely would work. But to get good results, I would recommend using the right pipeline.
Thanks.
Thank you. Do we have another question? I see a hand raised up there.
Thank you. Have you explored any transformer-based architectures like Vitae?
Like a vision transformer?
Yeah.
Yes. I kind of like working with vision transformers. And in general, you will be surprised how many learnings you can gain from typical computer vision models. Like when our pruning, for example, was initially developed for classical, like convolutional-based computer vision models. But pruning itself just means reducing the size of the network. And for vision models or vision transformer models, you have attention layers. And also in attention layers, you can prune maybe the input embeddings, the output embeddings, or the heads. And thus, the learnings you gain from computer vision can translate quite well, especially to vision transformers. But yeah, if you want to have any more details, I'll be happy to have a chat about this.
Thank you very much also for making yourself available for that. And then the time for question is over. We would like to really thank you.
Thank you so much.
And accept some flowers from us. We have an applause for Jonna Matthiesen. Thank you again.